Hello and welcome to another video on the Rationalist Scientist. Does science make mistakes? Science doesn't, but scientists may make errors. After all, to err is to be human, right? So what if I told you that Albert Einstein, generally regarded as the greatest scientist this world has ever seen, made a blunder, and that he himself acknowledged it? This story shows an intriguing journey from an apparent mistake to a renewed understanding of the cosmos. Today's video is all about the greatest blunder that Einstein made, and it is not his rejection of the quantum theory. I know the name Einstein and relativity can make some people leave the video here, but trust me, I will explain it as simple as possible without using any equations to confuse you. And the story has a shocking twist at the end, so don't miss to watch the whole video. I see that a lot of my regular subscribers have not subscribed to the new channel, so please subscribe if you wish to see the new videos earlier. Hello, I'm Anand and you're watching The Rational Scientist, the channel which promotes free thinking and scientific temper. In the vast expanse of our cosmos, our understanding of the universe has been shaped by the revolutionary insights of one man, Albert Einstein. Einstein, known for his brilliant mind and groundbreaking theories, reshaped our understanding of space, time, and gravity. In 1915, Einstein introduced the theory of general relativity, transforming our perception of gravity. For over 200 years, the physics of Newton appeared to govern how objects moved. Using Newton's laws of universal gravitation and laws of motion, we could determine how things moved on Earth, in a solar system, and in the greater universe. But when it came to things that moved very fast, like light, or when it came to big objects like the sun, the theory had a few shortcomings. For example, the movement of Mercury around the sun could not be fully explained using Newton's laws of gravitation. Now this was very insignificant in the grand scheme of things, but it troubled a patent office clerk in Bern, Switzerland. And in his free time, he came up with his general theory of relativity and his field equations. No, not this one, this one. And no, I'm not going to explain this equation here, so don't worry. But I want to point out one aspect of this equation, this sign. This Greek sign is called the lambda, and in this equation, it represents what Einstein called the cosmological constant. The equations explain how matter and energy warp the fabric of space and time to create the force of gravity. Once completed, it was natural for Einstein to apply his new theory to all of space and time. That is, to investigate whether general relativity could give a satisfactory model of the universe as a whole. He wanted to see it from start to finish and to see whether the theory had any contradictions. But the great scientist made a fatal error. And he made this error because that was the scientific understanding at that time. He assumed that the universe was static and not expanding. At the time, both Einstein and astronomers agreed that the universe was fixed in size and that the overall space between galaxies did not change. To force the universe to be static, Einstein attached the cosmological constant in the equation, just like that. His idea was to keep the universe from expanding using this constant, sort of like tying a dog to a leash. But the universe doesn't work on the whims and fancies of a single person, right? Another scientist by the name Willem D. Sitter worked with these equations and found something interesting. He came up with a solution that described a universe without any stuff in it, like stars or galaxies, but with this cosmological constant. His solution suggested that such a universe would actually expand and even speed up while doing so. But there was a problem. The De Sitter universe that he proposed was purely mathematical in nature without any direct observational evidence. Einstein disagreed with Sitter and they both had various debates on this topic and they never reached a consensus. Then came Alexander Friedmann. Using Einstein's theory of general relativity as a framework, Friedmann independently derived solutions to Einstein's field equations that describe the dynamics of the universe on a large scale. Friedmann's solutions indicated that the universe could be dynamic and changing. He showed that the solutions to Einstein's equations allowed for a universe that was either expanding or contracting over time. Once again, Einstein did not welcome Friedmann's contributions. His first reaction was that the Russian had made a mathematical error. Then came George Lemaître, who once again proved Einstein's concept of a static universe wrong by making astronomical evidence about receding galaxies. Apparently, Einstein did not consider this work in a favorable manner either. He simply stuck to his version of the universe and the cosmological constant. Nearly a decade later, another physicist, Edwin Hubble, discovered with better evidence that our universe is definitely not static, but expanding. The light from distant galaxies showed they were all moving away from each other. This revelation finally persuaded Einstein to abandon the cosmological constant from his field equations, as it was no longer necessary to explain an expanding universe. The Russian scientist George Gamow was said to have reported in his memoirs that Einstein once described the cosmological constant as his biggest blunder. That is the beauty of science. There are no authorities in science. Newton was once called the father of physics, but a clerk came and proved some of his theories wrong. And Lemaître and Hubble made Einstein acknowledge his mistake. That is the difference between science and religion. There is no superpower in science, and it is happy to change its theories and make even great minds realize their mistakes, provided that there is evidence provided. But the story is not yet over. For decades, the cosmological constant was sidelined, regarded as a blunder made by Einstein. It was considered an error made under the false assumption of a static universe by the great scientist. However, scientific inquiry persisted, and in 1998, astrophysicists uncovered an unexpected reality: the accelerated expansion of the universe. Observations of distant supernovae and studies of the cosmic microwave background radiation indicated that the expansion of the universe was not only ongoing but speeding up. Enter the concept of dark energy, an enigmatic force driving this accelerated expansion. Galaxies were accelerating away from each other as if some unknown force was overcoming gravity and shoving those galaxies apart. Physicists have named this enigmatic phenomenon dark energy, as its true nature remains a mystery. In a twist of irony, physicists once again reintroduced the cosmological constant into Einstein's field equations to account for dark energy. In the current standard model of cosmology, known as ΛCDM, the cosmological constant is interchangeable with dark energy. Astronomers have even estimated its value based on observations of distant supernovas and fluctuations in the cosmic microwave background. Although the value is absurdly small, it is significant enough to explain the accelerated expansion of space. This re-evaluation has transformed Einstein's supposed blunder into a crucial element of contemporary cosmology. The cosmological constant representing dark energy is now a key player in explaining the accelerated expansion of the universe, posing profound questions about the nature of space, energy, and the fate of our cosmos. In essence, what Einstein initially regarded as a mistake has evolved into an essential concept in our understanding of our universe. Today, Einstein's greatest blunder serves as a cornerstone of modern cosmology, and Einstein would be pleased in his grave. Lucas Lomreiser, an assistant professor of theoretical physics at the University of Geneva in Switzerland, has introduced a new way of evaluating Albert Einstein's equations of gravity to find a value for the cosmological constant that closely matches its observed value. The gravitational constant, which was first used in Isaac Newton's laws of gravity and which was also an essential part of Einstein's field equations, describes the magnitude of the gravitational force between objects. It is considered one of the fundamental constants of physics, eternally unchanged since the beginning of the universe. Lomreiser has made the dramatic assumption that this constant can change. In Lomreiser's modification of general relativity, the gravitational constant remains the same within our observable universe but may vary beyond it. He suggests a multiverse scenario where there may be patches of the universe invisible to us that have different values for the fundamental constants. But the problem is that currently there is no way to test this. But in the future, if experiments from other theories validate his equations, it could be a major leap in our understanding of dark energy and provide a tool to solve other cosmic mysteries. So remember the name Lucas Lomreiser. He could be the next Einstein. Now for the tail end of this video. This was not the only mistake that Einstein made. Towards the end of his scientific career, he was highly critical of quantum theory and dismissed it as saying God doesn't play dice with the universe. This shows that after all, he was just human and could make mistakes. I'm sure if he had listened to the evidence that Sattler and Friedmann had presented and decided to let go of his static universe concept, he could have discovered that the universe was expanding, and that would have been another feather in his cap. Einstein once made a famous quote that a person who has never made a mistake has never tried anything new. For in science, as in life, even the greatest minds find wisdom in their blunders. So I hope you like this episode. Please do the usual comment, like and share. If you like scientific content, please subscribe to this channel. I shall be back with another scientific tempo improving episode. Till then, keep questioning and keep exploring.